So we'll get cracking on. I'm sure you guys are looking forward to a coffee break in about half an hour's time. So yeah, my name's Nigel. Unfortunately, you have to listen to me twice today. Sorry about that. I'm here representing the non-MRI ways of imaging the brain. So first talk is going to be on electroencephalography, and I'll talk a little bit about magnetoencephalography as well, but not very much. And then this afternoon, well, later today, I'll give you a bit of a talk on brain stimulation. So this talk is actually pretty much going to follow a fairly similar path to the other guys. We're just going to talk a little bit about the technique itself, what it actually represents, what part of the brain we're sort of measuring with this technique. Then we can go into a couple sort of practical examples of how it's been used in psychiatry research. I'm a schizophrenia researcher, so I apologise. It's very schizophrenia biased, but hopefully that's not too much of a problem for you guys. Alright, so just a very, very quick history about EEG. It's quite an old technique relative to a lot of the other techniques that we're hearing about today. So the idea that the brain has these electrical properties was sort of first came about in sort of the late 1800s, where people actually started taking recordings from animals, particularly the rats and the monkeys. But it wasn't until 1912 was the first animal EEG, but it wasn't sort of until the mid-1920s that this idea was actually translated into humans. And it was this good-looking man here, Hans Berger, that first sort of had this idea. And it's quite an interesting story, actually. He was around the time of World War I, and he was actually off serving. And apparently he was a bit of a useless soldier, and he was sort of standing at the bottom of a hill, and this cart got detached from a horse and nearly ran him over, and he got quite badly injured. And his sister, who he had a very, very close relationship with, was many, many miles away, but got the sense that something was wrong and sort of very quickly wrote him an email saying, "Hans, you all right, you all right?" And he was really fascinated as to how this could actually take place. Like, he was miles away, there was no way that she could have known, but almost instantaneously had this idea. So he became very interested in the idea of telepathy. And so the whole idea of EEG was actually trying to measure how two brains could communicate without actually having any physical connection. Funnily enough, so he did his first recordings in around about 1924 and sort of saw this, what's now commonly known as the alpha wave. So this is a brain wave here, and this is just a sine wave down the bottom. But he wasn't really convinced himself, funnily enough. And it took him about 5 years to actually publish these results. And it wasn't until actually the mid-1930s when the rest of the scientific community actually took him seriously. He was actually considered quite a quack for quite a long time. So it wasn't until sort of some fairly well-known scientists picked up this idea and actually discovered, first saw some epileptic spikes, that this actually started to take up. And I guess from then on, epilepsy was sort of the main thing that EEG was used for. It was very much in the realm of the neurologists. But interestingly, in the mid-1930s, we actually saw some description of the EEG waves from some psychiatric populations as well. So the idea of using this has been around for quite a long time. Now I'm just going to take you back to sort of year 12 physics very quickly. I like to give you these reminders because I often forget this stuff myself, so it's probably more for me than it is for you, but it's good to know. So we're going to be talking a little bit about electromagnetism today, and probably with all of these techniques it's relevant. So just a bit of a reminder of some basic terms such as a voltage, which is just simply the electrical potential difference between 2 points. So this idea with a positive and a negative here, you get sort of an electric field running down here. The voltage is essentially the difference between 2 points, and the current is sort of the flow of electric charge between these points. What we get with any electric field is we also get the generation of a magnetic field. So if you all remember the right-hand law from physics, so if you get an electric field sort of running down this way, you get a perpendicular magnetic field which runs around here. Now this is going to be important for both this talk and for the next talk, so make sure you remember this basic principle. So the brain actually generates electrical activity, and it does this in a couple of different ways. So the first one, which everyone's heard about, now we're going to year 12 biology, so the action potential. So this is sort of a discrete voltage spike that travels from the cell body to the axon terminal. So it's essentially a really, really fast change in voltage. But the ones we're most interested in today are what are called postsynaptic potentials. So these are voltages that arise when neurotransmitters bind to receptors on the membranes of postsynaptic cells. And what this does is it causes ion channels, so either open or closed, and then leads to a graded change in potential across the membrane. So what does that actually mean? Essentially, when you've got a cell, so this is outside the cell, this is inside the cell, you've got lots of positive charges, positive charged ions on the outside of the cell, you've got more negative charged ions on the inside of the cell, so this creates an electrical gradient. We've got positive and negative, so if you remember again back to year 12 biology, membranes have a negative potential that rests at around sort of between 70 and 50, minus 70 to minus 50 was it microvolts, and then that can shift depending on where these ions flow. So you can either become more negative or become more positive, and these drifts sort of happen as the cells tick along. Importantly as well, the action potential timescale is very, very short, so these action potentials only last a couple of milliseconds, but these post-synaptic potentials can last up to hundreds of milliseconds, so they're quite long-lasting events. So what EEG does is essentially just measures voltage change between two electrodes over time on the scalp. So it's measuring scalp voltages essentially. In terms of what's generated by neurons, this is generally the summation of these postsynaptic potentials, and we'll go into this a little bit more in the next coming slides. However, it also includes any other electrical signal, and this is important to keep in mind. So this can be from anything from the muscles, from eyes, from movement, from equipment, from lights. So we've got all these other sources that can be contributing to this signal as well. And here's just a couple of examples. I particularly like this really high density one. This was from some kind of a meditation study. And this is essentially what you get when you look at the EEG signal. You get all these lovely squiggly lines. So what are we actually measuring in terms of neural activity? And this is, I think, something quite important to take into account when you're thinking about neurons, when you're thinking about sort of recording EEG. So there's two important things for EEG recordings in terms of neural contribution. First is geometry, and the second is timing. So most of the EEG signal actually comes not from inside cells, but it actually comes from the extracellular space. So that's what you're actually measuring. When you think about this, neurons are really, really tiny and there's lots of space around them. So, and it's the transmembrane potentials from cortical pyramidal cells which make the largest contribution to the EEG signal. And the reasons for this are those two factors, the geometry and the timing. So generally pyramidal neurons are arranged in this sort of a way where the dendrites sort of have two main parts. So we've got this apical region, which is out here, the cell body's down here, and this basal region, which is around the cell body. So then you probably have an axon coming off here somewhere. So the important fact about this is that the apical dendrites and the basal dendrites actually receive input from different cell populations. So what this means is, so if you've got a cell just sort of sitting at rest, you've got sort of lots of positive charges outside, more negative charges inside, at both this apical region and this basal region. So there's no real difference in terms of where all these things are, where all these charged ions are across this neuron. However, if we get an excitatory input, for example, into the apical dendrites, so this top layer up here, what happens is these positively charged ions flow into the cell, and then this now creates a difference in terms of the amount of positive or negative ions between the two. So you have more of a negative charge up here compared to a positive charge here, and this creates what's called a dipole. So this positive and negative charge here. Now these dipoles are really, really important, and you just see this is actually sort of some electric field lines taken from an actual cell here. So the reason that these dipoles are important is because of the geometry, how these cells are arranged within the cortex. So what actually happens is generally these pyramidal cells are sort of arranged in this kind of a manner along the cortex. So you can see that this is the top here, so you've got a gyrus up here going down to the sulcus and then back out. So what happens is if you get, say, some kind of input into the apical dendrites up here, you create these little mini dipoles, and you get lots of these little dipoles if, say, all of these cells here have been activated. Now, what this does is you've got the skull, the scalp, and then your EEG electrode sitting up here. These negative charges are actually closer to this electrode here, so we can actually record a difference, say between electrode number 2 over here, which nothing's really happened. So now I've got this negative here. It gets this negative stronger than it gets this positive, right? so it'll record this. What happens over here in say, in the wall of the sulcus is this positive and this negative charge of the dipole now are around about the same distance from our electrode. So these actually get cancelled out. So what this means is that we're actually recording with EEG mainly activity that's happening in the actual gyri themselves. So pretty much anything that's happening in the sulci mainly gets cancelled out. Now this is the main difference as well between EEG and MEG. So as we remember before from our right-hand rule, if we're getting these kind of electrical fields that are happening this way, we're also going to be generating a magnetic field which happens sort of in this direction. So with MEG, now we're getting the electrical field this way, the magnetic field going this way, and that's what MEG records from. So it's the main difference is that MEG generally gets activity from inside the solid walls, whereas EEG mainly gets activity from the gyri themselves. And again, basically just to really have this point home, all of this is reference dependent. So we're always looking at the difference between one electrode to another electrode. The other important point is the timing. So these are really, really small, okay? So in order to actually record these across the scalp, you need a lot of these to happen at the same time. So you need lots of dipoles to be happening at once. So the timing, the synchronization of a lot of neuronal activity is really, really important. And we saw from Paul sort of talking before about how many cells are contained within a 1 millimetre square. Generally, these electrodes are thought to be indexing activity from about at least a centimetre cubed of area. So you're getting a lot of grouped activity from lots of different cells. So another important point as well is that where we're recording these signals from is actually quite a long way from the source. So when you put these little electrodes on the head, you've got to get through the scalp, you've got to get through the skin. So you've got quite a fair bit of difference from the actual distance from the brain to the electrode. So this results in a really large attenuation of the signal from the source, which is the neural tissue, to the EEG electrode. So this is just some examples here taken in some animals where they've actually jammed some electrodes into the actual brain themselves and then recorded from the scalp as well. So this is sort of some of the source activity from actually within the brain, and this is the size of the activity that you're actually measuring here. It's probably even a better example of it over here, where you can see sort of from the scalp we're getting around about 150 microvolt signal, but in the actual brain itself it's around about 800 microvolts. So it's around about a five-fold decrease in terms of size. There's also a degree of spatial smoothing as well, which happens. Generally, any electrical activity takes the path of least resistance, and the skull itself is actually quite resistant. So what it does is it sort of spreads out the electrical charge. This is something really important as well. Okay, so as we saw, we got these nice squiggly lines across the scalp, and we've sort of successfully recorded an EEG recording. But what does it actually mean? What kind of information can we drag out from this? So generally we get these oscillations that we see, and we sort of saw that earlier when we saw those EEG traces, Hans-Berger's alpha wave. We get these oscillations that just sort of head across the brain. So generally what we're measuring when we're measuring from EEG is three main things. We're looking at either the frequency of the signal. So the frequency is how many cycles that we get within a time period, which is usually a second to give a hertz reading. So if we say that this is, for example, 1 second here, we have 2 cycles, that would be a 2 hertz recording. And we can also look at the amplitude of this. So this is the size here. So amplitude is just simply how big this is. So for example, this recording here is the same frequency as this recording here, but the amplitude of this one is much smaller than this one. So generally the frequency and the amplitude, particularly the amplitude, are thought to give us a sort of a basic idea of how synchronous the firing was of the neurons underneath. We can also look at the phase between 2 different signals, so between 2 electrodes. So phase tells us information about how 2 signals might be related to each other. So if there's sort of phase synchronization, if there's sort of a similar phase, you can see these peaks and troughs are roughly lining up between these 2. If there's no phase between the 2 signals, you can see there's sort of very little lining up of these peaks and troughs here. So what this gives us information on is can conceptualise as potentially some kind of neural communication. So we can get out some information here of what's happening between two different areas of the brain. Some typical sort of analysis techniques such as coherence have been sort of the mainstay of this field, but there's some more complicated analyses that are starting to come out now that are looking at sort of phase lags in between here to get more directed maps in terms of if an area is having an influence on another area. And there's also this idea of, I won't go into this too much, but of nested or of oscillatory coupling. So the influence of, say, a slower wave on a high frequency wave. So I don't know if anyone's familiar sort of in the memory literature at the moment, the big thing is theta gamma coupling. So the idea here is that the sort of the increase and decrease in excitability of these slower waves impacts faster oscillations potentially in another region. So you can see here the amplitude of this faster oscillation is getting bigger at these sort of high excitation periods and then getting lower at these low excitation periods. So this is quite a dynamic way of looking at brain activity. So as I mentioned, cortical oscillations, they've sort of been around for a very long time. There's just some recordings from back in the 1940s. But what generally happens, and what has happened over time, is that it's been noticed that different oscillation frequencies generally happen during different tasks, essentially. So some very basic taxonomy from very early on. We get these lower frequency delta waves that often happen sort of during sleep. These theta waves we just mentioned before tend to get a little bit bigger when people get drowsy. These alpha rhythms, which are really, really prominent in EEG recordings, happen when people are just sort of sitting around and relaxed. And then these high frequency beta and gamma oscillations often happen when people are actually doing something or engaged in a task. This is a fairly oversimplification, and this table here just gives you a bit of an idea of some of the different tasks that these different frequency bands have been associated with. And it's not just tasks as well, different places in the brain as well are thought to be more prominent for certain kinds of oscillations. So this is sort of one of the first examples in terms of how cortical oscillations have been used in psychiatry, and this is quite a hot topic at the moment in terms of the schizophrenia literature. So in post-mortem studies in schizophrenia, sort of from the mid-90s onwards, there's been this fairly consistent finding that various different cortical inhibitory machinery within post-mortem brains has been deficient, particularly around some of these fast-spiking inhibitory interneurons. And with a lot of computer modelling and now some sort of in vivo experiments using optogenetics in animals, people actually been able to tease out some of these networks and found that these recurrent excitation and inhibitory loops that are created between pyramidal cells and these particular inhibitory neurons result in gamma oscillations, essentially. So what happens is there's a heap of these cells, the inhibitory cells, that fire onto the pyramidal cells. They're inhibited for a little period. As they're released from their inhibition, they actually have a period of excitation, which excites both other pyramidal cells and back onto these inhibitory cells. So imagine you get excitation, which feeds into inhibition. So then the inhibition happens, and then they close down for a little bit, and then go back. And so you can see as that keeps looping around, what you get is an oscillation. And that sits in this gamma band very nicely. And this gamma band is actually increased in both animals and humans when they're engaged in something like a working memory task, for example. And working memory has been shown to be deficient in people with schizophrenia. And so they had this hypothesis that, right, if these inhibitory interneurons are actually deficient, we should see a decrease in this gamma band power in people with schizophrenia while they're performing the task. And that is exactly what they did see when they tested it. So it's a nice way that they've sort of been able to potentially link some anatomical findings into actual people with the illness that are alive. This isn't all of the story. It gets a little bit more complicated when you actually go on with the literature in a little bit more detail, but it's, I think, quite a nice example of a way that sort of EEG or MEG can sort of link various different findings in together. And just to show that it's not just for not just for memory tasks, this also happens in the sensory domain as well. So you can actually entrain different amplitudes of oscillations by giving, for example, an auditory stimulus at a certain oscillatory strength. So you can give, say, 40 hertz oscillatory tones. What you actually see in the EEG is a real spike of whatever frequency information that you're feeding in. And when you do that with patients with schizophrenia, again, these gamma regions, you see that they're much more reduced compared to some of the lower frequency bands. And this one over here is looking at synchrony. So how synchronous, in this case, beta oscillations are when you see this Gestalt image over here. These red lines indicate sort of decreases in synchrony between different electrodes in schizophrenia participants compared to people who don't have schizophrenia. So you can see there's quite a reduction in terms of synchrony, suggesting that sort of the connectivity and the ability of different neural areas to communicate with each other might be impaired for schizophrenia. 5 minutes, Alex. Struggle. We might be alright. Okay, so another way of looking at EEG is to actually stack different recordings up relative to a particular stimulus. This is what's called event-related potentials. So, for example, you might give a stimulus of some type here, say an auditory tone, it might be flashing up a light or something like that. What you do is you then cut out the activity directly after the stimulus, sort of stack them all up, and then you take an average. What the average does is it takes out any activity, cancels out any activity that's not related to the stimulus, so any noise or any sort of non-related neural activity. You get these quite nice, smooth-looking event-related potentials afterwards. And these peaks and troughs, again, are thought to give some kind of indication of the summation of activity of groups of neurons relative to different aspects of these tasks. This has been done over a long time. Some of these thought to directly reflect things like sensory processing or error monitoring, and there's a whole ton of in literature. So one that's been shown to be particularly, again, deficit in people with schizophrenia is the event-related potential that happens to what's called an auditory mismatch negativity. So this is like an oddball design task where you'll hear a tone of a certain frequency, and then after a while a discordant tone will be introduced. And when that deviant stimulus happens, you get this really big brain response. And if you keep doing this over time, again, you can sort of add this up and get this response here. Now, this has very, very robustly been found to be reduced in people with schizophrenia. There's actually a really nice model because it doesn't involve attention. It's not dependent on attention at all. So people just sort of sit there with headphones on and listen, and that's all they need to do to get this. And it's not just in people with chronic illness, but also in people who are at high risk of going on to develop schizophrenia. And it's actually reasonably good at predicting who will actually go on to develop schizophrenia. So people that have the deficit are much more likely to actually convert into the illness than people that don't have this deficit. So those are just a couple of real quick examples from the literature. I thought I'd just sort of finish up with a bit of a summary in terms of where EEG sits in terms of some of these modalities, in terms of advantages and disadvantages. Like most of these techniques, one of the real advantages of EEG is it's non-invasive. Where it sort of sits relative to some of these other functional techniques that you're going to hear about this afternoon is the excellent temporal resolution. So you can see we're measuring in the order of milliseconds. The brain's a very dynamic structure, it's changing very, very fast, and we're able to capture that with EEG. It's relatively inexpensive. We've had a question before about cost. The main cost with EEG labs is setting up the equipment. Once you've got the equipment to actually run the experiments, it's actually very, very cheap. You only just sort of need gel and a few consumables, and you're pretty much good to go. As well, the neural origins of the signal are reasonably well understood. A little bit of a dig at the fMRI guys here, compared to some of the other imaging modalities. Yeah, that's right, Alex. As I mentioned, fMRI, yeah, tell me the other side. Right. Some of the disadvantages, poor spatial resolution is the obvious one. They're trying to get around this a little bit now by high density montages. There's some quite fancy mathematics that's been used in terms of trying to figure out where the signal's coming from. Prevalence of artifacts is big. I didn't really talk about this much today, but as I mentioned earlier, any other source of electrical activity influences the signal, so it's separating out the neural signal from the artifacts can be quite difficult. The setup, although it's cheap, can be a little bit time consuming. As you imagine, putting gel into all of these different little electrodes takes time. And again, this idea that the signal is reference dependent. So whatever you're looking at is dependent on what you're comparing it to, essentially. So it can make it a little bit hard to compare things with other groups if you're not using the same reference. All right, any questions?
Sorry for the cost go again.
Sure.
How much is the setup of a lab cost?
Again, like it just depends on what system you get, what you're after. I'm not actually 100% sure, but it would be sort of in the order of sort of 10 or 15 grand, I imagine, to actually get a basic setup. Again, if you're looking for stuff that's sort of a bit higher end, the cost can blow out quite quickly. But yeah, I think, don't quote me on that, but I think it's around that.
I'm just going to keep asking the same sort of questions.
Sure.
Say you get a difference between two groups in terms of gamma power or something like that. What's the interpretation?
Yeah, so again, it comes down to this idea of groups of cells being able to synchronise activity. So that's essentially what you're measuring, is the synchronous activity of large groups of cells. And there's sort of didn't go into it today, but there's a whole theory in terms of how this synchrony is important in neural communication, how it underlies things like neuroplasticity and all of these other brain functions. And yeah, so it may be sort of the important thing in terms of the emergence of higher order brain functions. So it's this whole idea of the brain being able to communicate effectively is generally how it's interpreted loosely.
So then if you get differences in different frequency bands, are they kind of established heuristics? So for example, if you get a difference in gamma frequency, does that reflect just synchronization within the local area versus theta or delta, which is synchronization with long range? Or is it unclear?
It's interesting. So the gamma synchrony actually happens long range as well. It's generally thought that the actual the mechanisms that are generating the gamma are local, but you can get synchronization of gamma across large differences, and it could be due to this nesting of gamma within some of the other oscillations as well. The actual sort of mechanisms in terms of the circuitry mechanisms of some of the lower frequencies aren't as well understood as some of the higher frequency stuff, and that's only really come about in the very recent sort of last couple of years. So I imagine sort of over the next few years that's going to be quite an expanding area of research in terms of actually trying to understand the mechanisms, the direct mechanisms that result in the different frequency bands. But yeah, it's it's hard to interpret. It's like I guess like any of these techniques, because there's lots of different things that could be causing the differences.
There's no real clear mapping in terms of different frequencies to different functions, like cameras associated with this thing.
Yeah, I'll put up that graph before again. Like it's a heuristic, so they generally sort of match up, but you can get changes of these different frequencies with tasks that you don't necessarily expect. Or what happens in the literature a lot is people focus on one frequency band and just sort of ignore the others. So they generally do see changes in them, but they just don't focus their focus on them. So they happen, but yeah, it's a very, very complex interplay, particularly when you start thinking, like you can think about this in a linear sense in terms of gamma influences gamma. When you start thinking about it in a non-linear sense, the number of possibilities just become massive. So yeah, I think that's probably why most people focus down into specifics.
Just have a quick question. What sort of spatial resolution are we talking about, especially if you can do it with some fancy maths?
Yeah, so I mean, you can sort of. It's still not great. The whole. I'm being a little bit cautious just because it depends who you read and what you believe. So some of the people that come up with some of the source localization algorithms will have you believe that they can sort of get it down to sort of a centimetre cubed area to solve this. But yeah, I highly doubt that you're actually able to get that kind of a resolution. So you're looking over some quite broad cortical patch.
I think it's used for the surgery of epilepsy now.
So,
It's used for the surgery of epilepsy now.
yeah, so epilepsy is a little bit different. So in terms of when you're getting those really high synchronized activity like you do in terms of epilepsy,
You get a better resolution because it's
yeah, it becomes much easier because you're getting these really large signals.